Hello, everyone. Welcome back to this online class. Today, we are going to look at numerical solution of ODEs. We are going to look at boundary value problems, and in particular, we look at finite difference method. So we have this question. We are asked to use finite difference method to solve the following boundary value problem that is given by d squared y over dx squared plus x squared dy over dx minus 2y is equals to x, and the boundary condition at x is equals to 0, the value is 1, and at x is equals to 1, y is equals to 0. Take a step size of h is equals to 1 over 4 and compute the values of y of 0.25, y of 0.5, and y of 0.75 correct to 6 decimal places. So let's see how to go about this problem. Remember, when we talk of finite difference methods, we have 3 of them. We have what we call the central finite difference scheme. We have the forward finite difference scheme, and then we have the backward finite difference scheme. Now, if you look at our boundary condition, the starting point is at x naught, and the last one is at xn. I don't know because the step size is 1 over 4. So I don't know what is xn in this case, but we will know it. Let me draw this kind of a line to explain what you mean. That at this point, we are starting from x0 all the way up to the last one is x is equals to 1. And we know the value of y when x is 0, the value of y is 1. And when x is 1, y is 0. But because we have a step size of 1 over 4, so from 0, because we are saying these are the x values, this is x naught. The next value here will be, you're adding 1 over 4, so that is 1 over 4, followed by, add 1 over 4, you get 1 over 2, continue adding 1 over 4, you get 3 over 4, and then when you add 1 over 4, you'll get 1. So this is x naught, this will be x1, x2, x3, and this is x4. So our n in this case is 4, xn. So I can write here x4. It will depend on the interval h. Now, one here is y naught, and this other one is y4. I don't know the value of y1, y2, and y3. So you put a question mark. I need to find y1, y2, and y3. Remember, when we write y1 is the same as y at x1, which is y of 1 over 4. 1 over 4 is the same as 0.25. 0.25. We don't know that. We'll find it. When we write y2, we mean y at x2, and x2 is 1 over 2. That's y at 1 over 2, which is 0.5. Y of 0.5, we'll find that. And we'll also need to know what is y3, which is y at x3. And our x3 is 3 over 4, which is the same as 0.75. So, let me show you how to find those values. So, our ODE can be rewritten as, in terms of prime notation, as y double prime, remember they are functions of x, plus x squared, let me write this way, y double prime of x plus x squared, y prime of x, minus 2y of x is equals to x. I am writing the same ODE in terms of the prime notation. The next step is to evaluate the ODE at x is equals to xi. Evaluate the ODE at x is equals to xi. So what you're going to get is this one. It will now be y double prime at xi plus xi squared y prime at xi minus 2y at xi is equals to xi. And take note that I want us to write a note here that when I write y at xi, it is the same as yi. When we write y prime at xi, it is the same as yi prime. And when we write y double prime at xi, that's the same as yi double prime, etc. So we can rewrite this as, can say, or this can as well be written as yi double prime plus xi squared yi prime minus 2yi is equals to xi. So once you have your ODE evaluated at xi, you now approximate those derivatives using either central difference scheme or forward difference scheme or backward difference scheme. I want us to use central difference scheme to approximate the derivatives. So you can write using central difference scheme, we have, let's start with the first derivative. yi prime is the same as yi plus 1 minus yi minus 1, everything over 2h. For the second derivative, yi double prime is the same as yi plus 1 minus 2yi plus yi minus 1, and this is now over h squared. So we will substitute them back into this equation, the one I'm calling star, and then we simplify. So our equation star becomes, you can say hence, equation star becomes, it will now be yi plus 1 minus 2yi plus yi minus 1, everything over h squared, that is the second derivative, then plus xi squared into yi plus 1 minus yi minus 1 over 2h, then minus 2yi is equals to xi. Let's multiply through by h squared. I want us to simplify. So when I multiply by h squared, I'm going to get this yi plus 1 minus 2yi plus yi minus 1 plus h squared xi squared over 2h into yi plus 1 minus yi minus 1 then minus 2h squared yi is equals to h squared xi. And I can simplify. Look at this one. H squared over 2h is the same as writing h over 2. So I can rewrite this as h over 2 times xi squared. So let me rub it. This you can write as h over 2 times xi squared. So I'm going to rewrite it. H over 2 xi squared. And so I can now collect the like terms. Let us collect the like terms. We start with yi minus 1. So here we have 1 minus, this other one is h over 2 xi squared. H over 2 xi squared. These are the coefficients of yi minus 1. Then I now need the coefficients of yi. Here we have negative 2, and here we have negative 2h squared. So that's the same as negative 2 into 1 plus h squared yi. And those of yi plus 1, here we have 1, and here we have h over 2 xi squared as a positive. So it's plus 1 plus h over 2 xi squared. The coefficients of yi plus 1. On the right hand side, we have h squared xi. So remember, we know the value of h to be equal to 1 over 4. So the next thing, you put h is equals to 1 over 4, and then you simplify what we have here. So you can write put h is equals to 1 over 4 to get. Now with 1 over 4, we are going to get 1 minus 1 over 8 xi squared yi minus 1. Then here we'll have minus 2 into 1 plus h squared is now 1 over 16 yi plus 1 plus 1 over 8 xi squared yi plus 1 is equals to 1 over 16 xi. And if I simplify this further, I am going to get, you can write or, here we'll have 1 minus 1 over 8 xi squared yi minus 1 minus 17 over 16 and 17 over 8 because of the 2 there. So 17 over 8 yi. Then the other one is plus 1 plus 1 over 8 xi squared times yi plus 1. That should give us 1 over 16 xi. So this one is what you are calling the central difference scheme. Let me bracket it. Central difference scheme for the given boundary value problem. Remember, when you talk about boundary value problem, is you're given an ODE together with the boundary conditions. So this is central difference scheme, or simply the finite difference scheme. Finite difference scheme. So that scheme will help you get the missing values of y, the y1, y2, and y3. So when you go back to whatever I had drawn, let me take you back. You realize that whatever we have here, we don't know the value when I is 1, and when I is 2, and when I is 3. So we are going to iterate through from I is equals to 1, 2, all the way up to 3. So when we come back here to our scheme, you write for I is equals to 1, 2, 3. We are going to iterate 3 times because we have 3 unknowns. So let's start with the first iteration when I is equals to 1. So you can write put I is equals to 1. What are we going to get? It will give us, let me write it here. That is 1 minus 1 over 8 x1 squared y naught minus 17 over 8 y1 plus 1 plus 1 over 8 x1 squared y2. That should give us 1 over 16 x1. And you know the value of x1. Let me take you back to what we had drawn. X1 here is 1 over 4. That's what we are going to substitute. It is this value here. X1 is 1 over 4. So let's go back and replace it. So you can say put x1 is 1 over 4. X1 is equals to 1 over 4. What will it give us? That should give us 1 minus 1 over 8 times 1 over 4 squared. And remember, we also know y naught, or let me just write y naught minus 17 over 8 y1 plus 1 plus 1 over 8 1 over 4 squared y2 is equals to 1 over 16 times 1 over 4. And so when you press this in your calculator, let us simplify this further. You need to get 127 over 128 y naught minus 17 over 8 y1 plus 129 over 128 y2. And on the right hand side we get 1 over 64. If I multiply through by 128, we write multiply by 128. We are going to get, that should be able to give us 127 y naught, you can write or, minus, the other one will give us negative 272 y1 plus 129 y2 is equals to 2. And we know the value of y naught, so this is known because it is given from the boundary condition. So it is known. The y1 and y2, we don't know them. So what we know, let's replace it. So put y naught, what was it? Look at your boundary conditions or whatever we drew here, that our y naught was equals to 1. So we know the value, so we are going to substitute. Where there's y naught, we put 1. So what will it give us? Finally, that should now give us, we are substituting 1, remember. So it means I'm going to take it to the right hand side so that what I remain with is negative 272 y1 plus 129 y2. So we'll have 2 minus 127, which is negative 125. So this is the first equation. Let me bracket it. And the first equation, you call it equation Roman 1. The second iteration is when I is equals to 2. So next we put I is equals to 2. I is equals to 2. In the same finite difference scheme, look at the scheme. Now when I is equal, we are through with when I is equals to 1. Now we are back to when I is equals to 2. What are we going to get? It will give us, let me write it here. It will give us 1 minus 1 over 8 x2 squared y, now it is y1 minus 17 over 8 y2 plus 1 over 8 x2 squared y3. On the right hand side we have 1 over 16 times x2. We know the value of x2, so we can replace it. Our x2 is 1 over 2. Let me take you back to where we defined it. This is our x2, which is 1 over 2. So in place of x2, I'm going to write 1 over 2. So I take you back. You write here, put x2 is equals to 1 over 2. x2 is 1 over 2. So what we are going to get is, now it is 1 minus 1 over 8 times 1 over 2 squared y1 minus 17 over 8 y2 plus 1 plus 1 over 8 into 1 over 2 squared y3. That should be able to give us 1 over 16 times 1 over 2. If I simplify, I'm going to get, on the first term will give us 31 over 32. 31 over 32 y1 minus 17 over 8 y2 plus 33 over 32 y3. On the right hand side, we need to get 1 over 32. So we can multiply through by 32 to get, you write multiply by 32. So that you are going to get 31 y1 minus 68 y2 plus 33 y3. That should be able to give us 1 on the right hand side. We don't know y1, y2, and y3, so this will form our equation 2. So let me bracket it. You can write this is equation number 2. And we bracket this equation. And finally, we need to know what will be the equation when I is equals to 3, because we said we are iterating 3 times. So then the last one, you write put I is equals to 3. Put I is equals to 3. Again, you go back to our finite difference scheme. We now substitute I is equals to 3 and see what you're going to get. So when you do the substitution, this is what you'll get. It should give you 1 minus 1 over 8 x3 squared y2 minus 17 over 8 y3 plus 1 plus 1 over 8 y, not y4, but that should be x3 squared, then times y4. On the right hand side, we have 1 over 16 times x3. Now we know the value of x3, so you write put x3 is equals to 3 over 4. So what we'll have here is, you can write or, now we have 1 minus 1 over 8 times 3 over 4 squared y2 minus 17 over 8 y3 plus 1 plus 1 over 8 times 3 over 4 squared y4 is equals to 1 over 16, and our x3, that is 3 over 4. If you simplify, you need to get, the first term is 119 over 128. 119 over 128 y2 minus 17 over 8 y3. The other one is 137 over 128 y4. And this equals to, on the right hand side, you need to get 3 over 64. I can see 128 is common in the denominator, so we can multiply through by 128. So you write multiply by 128 to get, you write multiply by 128. So this is what you're going to get. 119 y2 minus 272 y3 plus 137 y4 is equals to, on the right hand side we'll get 6. We know y2, we don't know y2, we don't know y3, but we know y4. So y4 is known. Whatever is known, you can replace it. So this one is known. What was the value of y4? Go back to our diagram and check the value. That is the boundary condition at the other end. And we said from our diagram, y4 is equals to 0. So I'm going to substitute 0 where there is y4. So with that, let me take you down now to our equation. And you write here, put y4 is equals to 0. Put y4 is equals to 0. So what we are going to get is that 119 y2 minus 272 y3. That should give us 6. And so this is the third equation, equation Roman 3. So let me bracket it. Now we have how many equations? There are three. Three equations in three unknowns. Solve the three equations simultaneously to get the value of y1, y2, and y3. I believe you can solve the three equations. Remember, you can use any method, either elimination method, substitution method, matrix method, whichever method, Cramer's rule, as long as you'll be able to find the values of y1, y2, and y3 using the shortest method possible. So I'll just write here that solve equations Roman 1 all the way up to Roman 3 simultaneously. Solve 1 to 3, 1, 2, and 3 simultaneously to get, when you do that, you need to get your y1 is equals to 0.612338, 612,338. Y2 is equals to 0.322138, 22138, and y3 is equals to 0.118877. Remember, we are rounding off to 3 decimal places. So this value here is the value of y when x is 0.25. This other one is the value of x, not x, but value of y when x is 0.5. And this other one is the value of y when x is equals to 0.75. So that's how to use finite difference method to solve a boundary value problem. So thank you all for watching this video. Please subscribe to my YouTube channel, that is Professor Francis Okech. When you go to the YouTube search, type Francis Okech or Prof. Francis Okech, and you will find me right there. Also, don't forget to comment, like, and share this video. When we meet next time, we look at more problems involving boundary value problems. Bye-bye.